Now let's consider another example. This is about the distribution of photoreceptors on the retina. Let's first look at some data. This data plots the density of photoreceptors on the retina. Let's just look at the density of the cones. The cone density is this red curve, okay? And ignore this blue curve, which describes the density for the rods. You see that this density is very high at this location, fovea. Okay, fovea is the center of your visual field. The density really high. And this density drops very, very sharply, very quickly as you leave away from the fovea, yeah? And here the distance from fovea is measured by visual angles, okay? And so 0 is the center. And when you go all the way to 80 degrees from the center, this is very far away in your periphery, okay? And so because the center is more dense, you can have higher visual acuity. This is less visual acuity, and you can visualize this visual acuity in this chart, okay? So how do you do that? You fixate your eye gaze at this center dot, okay? Try not to move your eyes, no cheating, fixate there. And then trying to see each letters without moving your eyes. You can see that each letter normally, if your eye vision is kind of on average, you should see that each letter is equally legible or equally clear to you. So for the letters near the center, they are very clear to you, even though they're very small. But for the letters, far away in the periphery, okay, keep fixating here, they are just about the same legibility. If they become smaller, you may not be able to read them so well, okay? So anyway, so for efficient coding, we may ask, can we understand why is this particular cone density distributed this way? Can we understand from the efficient coding principle? Yeah, okay. In this case, S is the image location X of a relevant visual object on the retina. O is the identity or the index or label of the cone most excited by this object. And so this cone reports where the object is. So when it's excited, it says the object is right here at where it is, yeah? And our K is that our design where to place these cones on the retina to sample the object location X. And let's again consider the low input noise situation so that the image location on the retina is very clear. And that means we again need to use maximum entropy coding. So now let's record the thing we just learned for the fly's contrast response function. And here we notice that we designed the contrast response function such that we put the most sensitive part of the response function to where the most likely contrast input might occur, yeah? And so this means we are allocating a lot of possible output response levels, this level, that level, that level, different output response level, lots of possibilities for a small range of input contrast. This is because within that small range, it's more likely to happen. So that means this function really is indicating the density of output response levels, and this density should match the probability that input contrast happens around there. And so we can make this same analogy to our cone sampling, okay? And so the maximum entropy coding means we need to make the density of cones to match the distribution of objects on our retina. So if the objects on our retina are more likely to appear at the fovea, then we need to have a higher density at the fovea. So what is the probability density of objects on the retina? Here, let me just explain the intuition without going through the mathematical derivations, which you can look up in the book. So the idea is that a priori, the objects can appear anywhere on the retina. For example, this is the retinal space, so all the retinal locations, and these red dots are samples of object locations on the retina. They can be anywhere. Okay, and I should point out that we consider the case that each time there's only one object on the retina. You may say that this is not right. We have many objects in our visual field. They all fall onto our retina. So here I'm assuming that you are paying attention to only one object and ignore other objects. And so therefore only one object is relevant. Other objects do not count. And this is an assumption or simplification for us to understand the cone density. And so let's continue. So consider that only one of these objects are on the retina, and this is just the possible locations this one object may appear. Could be here, could be here, could be there. So let's say this one, okay? And then this one object, because we're paying attention to it, it's not in the center of vision, so we move our gaze towards it, okay? After we move our eye toward it, this object will fall closer to our fovea. So this is how this object location after gaze movement will fall towards here. If it's that object, after gaze movement may fall here, and so on. So these blue dots are the samples of object locations after we move our eyes to it. Yeah, okay, so these are the samples. And so they are not exactly at the center of our visual field. They are not exactly falling on the fovea. This is because our eye movements are not very precise. So when we move our eye towards a target, we will sometimes land exactly onto a target. Our gaze land exactly onto it, but most of the time it's just close to the target. And so that's why it's kind of the object location after gaze movement is close to the fovea, but not exactly the fovea. And so this is the object location after the movement. This is before the movement. And if you combine them together, this is the overall probability of objects on our retina. Okay, of course, sometimes when it's not very close, you may move again to get them closer. So you may do more than one eye movement to get the object closer to your retina. So in the end, you can calculate what exactly is the probability of the object locations on the retina, considering the property of eye movements, how precise they are, and how likely we move, and so on and so forth. Yeah, and so this is how you can derive the probability density of object locations on the retina. And then you can compare this density with the cone densities to see if they match. Now, qualitatively, you see that this does make sense, yeah? Okay.